Okay, so before I give you the definition of conditional probability, let us look at this problem. A dice is thrown. What is the probability of getting a prime number? And what is the probability of getting a prime number given that an odd number has occurred? So in this example, the first part is the unconditional probability, because we are simply to find out the probability of getting a prime number without any condition or without having any prior information or nothing. But in the second part, to find the probability of getting a prime number given that an odd number has occurred. So here we are to find the probability of a prime number on condition that we have some prior information. And what is that prior information? An odd number has already occurred. So this is the conditional probability. To find the probability of a prime on condition that to find the probability of getting a prime on condition that an odd number has occurred. Now the sample space when a dice is thrown, 1, 2, 3, 4, 5, 6, I declare an event B as getting a prime. So how many primes are there? 2, 3, 5. So definitely the unconditional probability, that is the first part, is number of favorable outcomes, that means 3 upon total number of possible outcomes, this is 6, and half. Result is half. Now for the second part, you see, given that an odd number has occurred, let us declare an event A as getting an odd number, event of getting an odd number. So how many odds are there? 1, 3, 5. Now we are to find probability B given A. What's the meaning of B given A? The probability of the occurrence of the event B given that the event A has already occurred. That means the probability of getting a prime number given that or known to us that an odd number has occurred. Now here you see what will be the number of favorable outcomes and what will be the total number of possible outcomes. Now if it is known to us, if we have the prior information that an odd number has already occurred, that means the given probability is nothing but to find the chance of getting a prime number out of the odd numbers only. This probability is nothing but to find the probability of a prime number out of the odd numbers only, because we have the prior information that an odd number has occurred. That means out of these odd number, how many primes are there? 3 and 5. So this is the number of favorable outcomes. And what is the total number of possible outcomes? Here, as we have the information that an odd number has already occurred, so the total possible odd numbers, this is the total number of possible outcomes. So here the sample space is reduced to A. In this conditional probability, the original sample space S has been reduced to A. So A is the new sample space. So we write P B given A equals to 2 by 3. That means probability of getting a prime number out of the odd numbers. Now see how to formulate this one. We have written P B given A equals to N B intersection A. That means number of outcomes in the set B intersection A. So what is B intersection A? B is the set 2, 3, 5 and A is the set 1, 3, 5, and their intersection is nothing but 3, 5. That means number of favorable outcomes is 2. So here we write NB intersection A upon NA. So the sample space, this A is the reduced sample space. Now see, if both in numerator and denominator, if we divide by NS, then what happens? NB given A divided by NS, and here also NA upon NS. And what is this? NB given A NB intersection A divided by NS. This is nothing but PB given A, and this is NA divided by NS. This is PA. So this is the definition of the conditional probability. Probability B given A equals to probability B intersection A divided by PA. Similarly, we can write probability C given D. What will be probability C given D? Probability C intersection D upon probability C. What will be probability A given B? This is probability A intersection B divided by probability B. That is. Now, as here it is given that an odd number has occurred. Now, if an event has already occurred, its probability is non-zero, definitely greater than 0. So in the definition of conditional probability, we write PB given A equals to PB intersection A upon PA, comma PA not equal to 0. Why shall you write PA not equal to 0? Because the event A has already occurred. See the definition of conditional probability. If A and B, the two events, such that PA not equal to 0, then the conditional probability of B, given that A has occurred, is defined as PB given A equals to PB intersection A or A intersection B, same thing, divided by PA, and definitely PA not equal to 0. This is up to this the definition. Similarly, if PB not equal to 0, the conditional probability of A given B is defined as PA given B equals to PA intersection B divided by PB, comma PB not equal to 0. That's it. Independent events. Two or more events are said to be independent if the happening of one event does not depend anyway in the happening or non-happening of another event. For example, if I toss two coins, then the event of getting head on the first coin is independent of the event of getting head or tail on the second coin. And mathematically we define as an event A is said to be independent or stochastically independent if probability A given B is equal to the probability A. That means if A and B are independent, then whether B happens or it doesn't happen, it has no effect on the occurrence of A. So simply PA given B is equals to PA. That means if the conditional probability becomes equal to the unconditional probability, then we say that the events are independent.